Thanks for tuning in. Today we have Jamie Douglas talking through eccentric exercise, physiological characteristics, and acute responses. So, welcome, Jamie.
Thanks, Rob. Good to be here.
Okay, we're going to try to get this done in 15 minutes, and obviously, it's been a review paper. There's plenty to go through, but do you just want to give us a little review of the review?
Sure. So this is the first paper from my PhD, and basically it's the first of, for lack of a better term, a two-part series. So it's a narrative review of the physiological characteristics of eccentric contractions and exercise, as well as the acute responses. The main thrust was basically to give a broad brush overview of eccentric exercise, sort of setting the scene for some of the chronic adaptations, which we cover in the second review.
Cool. Do you just want to dig a little bit deeper and maybe get into a little bit more about the review?
Sure. Yep. So basically, we have a bunch of different areas, and as I mentioned to you, we could sort of delve into each of these areas in a fair amount of detail. But basically, we have our introduction, and then the first, review section is looking at the characteristics of eccentric contractions. So initially, we have the molecular characteristics, and then the neural characteristics. And then the bulk of the review looks at the acute responses to eccentric exercise. So we cover neuromuscular responses, cardiorespiratory and fatigue responses, and this could just as easily be referred to as, metabolic responses, the hormonal responses, and then some of the more direct anabolic signaling or molecular responses. And then finally, we look at muscle damage and the repeated bout effect. And that's basically the thrust of it.
Excellent. So I know you've got some summary slides. Do you just want to run through them and let us know what came out the back end of this review?
Yeah, absolutely. So probably a good place to start here. Effectively, we wanted to figure out, why are eccentric contractions different? And there's a bunch of literature out there, a bunch of papers. But just to start with, setting the scene, there are a number of phenomena at the molecular level that would indicate that the cross-bridge theory of contraction is inadequate in explaining what's happening during eccentric contractions. So first of all, we see a greater tension-generating capacity at the level of the sarcomere. We see a reduction or a reduced energy cost per unit of mechanical work. So effectively, less ATP is required per unit of mechanical work. We also see a time-dependent residual force enhancement. So what that means is that if an isometric contraction is immediately preceded by an eccentric contraction, we do see an increase in the amount of force that can be produced. And interestingly enough, we don't really know to this day why we're seeing these deviations from the predicted model, but there are a number of theories, hypotheses floating around. So first of all, it's thought that the number or proportion of cross bridges bound at any given time is greater during lengthening contractions, or a change in the X distance, which you could refer to as the lever arm for each individual cross bridge. In terms of explaining the reduction in energy costs, it's thought that cross bridges become suspended in an actively bound state and they're mechanically detached. So with isometric and concentric contractions, the unbinding of the cross bridge is energy intensive, requires ATP, and it's thought that they're just pulled apart, which reduces this energy cost. And lastly, and I guess is kind of new territory that's being explored more and more, is looking at the molecular protein or the structural protein titin. And there is evidence that during eccentric contractions, titin is activated and possibly even winds upon actin, thereby serving effectively as a molecular spring. So each of these, mechanisms could contribute to the above phenomena to varying degrees.
Nice. Do you just want to just flip to the next slide? Because I know you've got something coming up which just takes us a bit more in depth in this.
Yep. So in terms of the neural characteristics, we do see a greater and distinct activation of the motor cortex. So basically, a greater brain area is activated. This is during submaximal and maximal eccentric contractions. Interestingly enough, there is a reduction in muscle activation. So at the level of the motor unit, there does appear to be an inhibition, especially in terms of discharge rates. So it's thought that there is a spinal dysfacilitation, effectively just serving as a handbrake. So in terms of this figure on the left, I think this is a nice representation of this phenomena. So this is 3 sets of 7 eccentric and concentric isokinetic contractions. And we can see that the force produced or the torque produced is markedly higher during our eccentric versus concentric contractions. However, muscle activation, as inferred from electromyographic activity, is markedly lower. And if we don't have this inhibition at the level of the spinal cord, this difference could potentially be greater, and we could be producing more torque eccentrically. So there's some interesting mechanisms going on there. And lastly, in terms of these neural characteristics, it was for a wee while thought that the size principle is reversed. So it was proposed that high threshold motor units could be preferentially recruited. So a study in '88, they did demonstrate this, and in a follow-up study, they found a preferential recruitment of fast twitch synergists within the triceps surae. But there's been a fair few studies since then that haven't been able to corroborate this. So we do think that the size principle probably does hold during eccentric contractions. So I guess just moving on from these contraction characteristics, we do know that we see some, novel acute responses to eccentric exercise. So first of all, just jumping into the neuromuscular responses, we see 20 to 60% more torque produced. And this observation does tend to hold across single joint and multi-joint movements. And because of this higher torque producing capability and the inhibition of motor unit recruitment, we see a markedly higher torque per active motor unit, which we do think has implications for some of these responses down here, which I'll get to in a moment. And lastly, we see a unique force velocity profile. So I'll just flick back to the paper quickly. Okay, so on the right here, we see our typical concentric force velocity profile. So with increasing angular velocity, we see a reduction in the amount of force that can be produced or the amount of torque at the joint. However, with increasing negative angular velocities or eccentric velocities, there's an increase up to a point followed by a plateau. So this indicates that the highest eccentric forces can be produced at the highest angular velocities. Okay, in terms of the metabolic responses, we see 4 to 5 times less oxygen consumed for a given mechanical workload, and correspondingly around about half the cardiac output is required. And the fatigue response, whether it be endurance type eccentric modalities, so eccentric cycling, downhill treadmill walking, or even isokinetic resistance training, effectively far less fatigue for a given sort of session workload and even at higher workloads. So we think that has implications to how much work can be performed per session. But again, that's a little bit speculative as we don't know, I guess in terms of the overtraining response, the effect that really driving this workload up could have. And just coming across to the acute hormonal responses, across the board in terms of testosterone, growth hormone, IGF-1, insulin, and cortisol, pretty equivocal in terms of the differences between eccentric and concentric contractions. Possibly higher IGF-1 response if the eccentric phase is sufficiently loaded, so it's not constrained by concentric strength. But the point I want to make is there's a growing body of evidence to indicate that the acute hormonal response to a resistance exercise bout perhaps isn't particularly important for the long-term adaptive response. And what we're probably more so interested in would be what's happening in terms of the molecular signaling response. And we do see with eccentric contractions versus concentric and also versus insufficiently loaded traditional resistance training, a greater satellite cell response. So it's thought that this more marked satellite cell response is related to the signaling cytokine interleukin 6. And we know that the magnitude of satellite cell activation has pretty important implications for the overall hypertrophic response to resistance training. And we also do see greater protein synthesis through these more direct anabolic signaling pathways. And interestingly enough, both of these effects appear to be more marked in type 2 or fast twitch fibers. And just coming across to molecular damage, due to these high strain rates, we do see greater exercise-induced muscle damage to the extent that it's actually quite hard to attain any marked level of muscle damage in the absence of eccentric contractions. And we also see a markedly higher muscle soreness response. And again, this damage response does appear to be most prominent in type 2 fibers. So I guess just in summary of all those acute responses, we do tend to see a novel adaptive signal within the neuromuscular system. So I guess that's the thrust or the bulk of the review, and we like to think that it sets the scene for some of these chronic adaptations that we do see. So just to bring it back to the top and I guess bring it all together, the key points that we took from this were that eccentric contractions, where muscle is actively lengthened under external load, do display a number of molecular and neural characteristics which distinguish them from isometric and concentric contractions. The distinct characteristics of these contractions do have a number of physiological implications for eccentrically biased exercise and subsequently the acute responses to exercise. And finally, the characteristic responses may be related to an adaptive signal within the neuromuscular system that we don't see with concentrically biased or traditional resistance training that I guess is constrained by concentric strength. So yeah, that's effectively the thrust of it.
No, that's brilliant, mate. Thank you very much for doing that and going through that. Are you in a position right now to give us some kind of practitioner takeaways, or is that going to come in the second part of the review? Because I know that's obviously a big part of it.
So the main takeaways from this were, I guess, generating the direction of the chronic adaptation. So it was more so to explain why we're seeing some of these novel adaptations, and also to, I guess, inform around some of the damage responses and the repeated bout effect as well.
No, that's all good, mate. So we can look forward to part 2.
Yeah, absolutely.
Brilliant. So where can people get hold of this paper?
So it's on SportsMed, but I'm also on ResearchGate as well. So if they want to contact me on there, I'm more than happy to share it.
Great. And you're quite active on Twitter, putting your published papers out there?
Yeah, absolutely. Yeah, so I'm on Twitter.
And what's your Twitter account, Jamie?
It will be Jamie Douglas NZ.
Jamie Douglas NZ. Perfect. So we are coming to 15 minutes, so bang on time. Really appreciate you doing this, mate. Thanks a lot again, and I'll speak to you soon.
Cool. Thanks, Matt.
Thanks, mate.